screen as well. 2 minutes ago, that was like, and I managed to fix it. So let's get started. So if you have, yeah, reload your screen and for you to take your own notes, please go ahead and do that. Let me just start it. So the correct version will have 29 content slides. There's a few unused slides at the end, which I'll fix later. So that's that. Here's we are in week 8 also, so the course is speeding up through there's always the feeling of speeding up through the second half of the semester. Quiz 2 is out and it's due this week. I'm already seeing more than 130 of you have started. Not many have finished. So hopefully it helps you to refresh some of the content from weeks 3 to 6. Assignment 2 was just out. There was one bug fix in the code. If you spot more bugs, do let us know on Piazza. Video assignment is out. So after this lecture, in the next 3 lectures, we're going to move to graphical models and then come back to approximate inference. So after graphical models, we'll sort of take a break from the Bishop book and hear from our guest lecturer who has wonderful experience using machine learning industry for many years. And he will talk about ML insecurity in particular, David Leibowitz. He's really great. So here is what we are going to do today. So the forecast it's a little bit technical, but it touches upon a very important topic on approximate inference. And then we'll use the trick we just learned, namely Laplace approximation, to as a weapon to help us to figure out how to do classification with Gaussian processes. So this lecture sort of ties together a number of content that we have looked at before, such as logistic regression and even more Gaussian distributions. So I know we had a lot of that last week, but since we're doing both Bayesian inference and Gaussian process, there will be more Gaussian distributions coming. So a note, so we wouldn't be explicitly referring to the Gaussian process book this time, but the corresponding content is in the front part of chapter 3. So far, we've talked about distributions and integrating them, marginalizing them, using Bayes' rule to manipulate them one way or the other, and compute the, let's say, posterior distributions of a prediction a lot. And we have always been assumed we're able to marginalize out things. Even if we can't do analytically, we might be able to do numerically. So approximate inference is this general class of techniques where we, instead of say, well, let's just resort to numeric integration or sampling or any of these tricks, which we might touch upon at the end of this class, let's try and find a probability distribution that is not exactly what we're looking for, but close enough in some sense. Right, in this particular case, we would like to find a Gaussian approximation. The goal is to find a Gaussian approximation to a probability density function defined over a set of continuous variables. And the method for doing this seems really naive, right? So if we have a non-Gaussian distribution, let's say it looks like this. It's a bit lopsided. Right? So we have x, p of x, like this. So the approximation is to basically find a mode, basically maximum point in p of x, and then just center a Gaussian around it. And you can say, oh, we just center Gaussian around it. There might be this Gaussian, or there might be this Gaussian, or something else, right? So we know that the mode of the Gaussian matches the mode of the original, like P of X. In the book is denoted the P of Z and Q of Z. In this slide, we haven't prescribed how the variance of the approximating Gaussian is decided yet, but that comes in the next slide. Right. So let's first say that consider a P of Z where it's in the form of some function over a normalizing factor where this fact, so to ensure that the PDF integrates to 1. It's just written this way because deciding on the normalizing factor can be difficult, as we will see in the next week or two, especially in graphical models and in other more complex distributions. But for now, let's just assume the P of Z has such a form. And we know F of Z, which is unnormalized distribution. So in the next page, we're going to just work with this unnormalized distribution. So this content is going back in chapter 4. So we're going to go through most of chapter 4.4 and 4.5 before coming back to the Gaussian process section. Excuse me. Sorry if the mute doesn't work. But anyway, well, let's continue to look at this F of Z. And the goal is to find a Gaussian distribution, and the necessary and sufficient condition for a distribution being Gaussian distribution, let's say Q of Z, being Gaussian is that the log of Q is a quadratic function of Z. We can easily see that from this, well, by reminding ourselves of the Gaussian PDF expression on the right. And we already said we would like to have the mode or maximum of the two PDFs match. So let's first find it. Let's assume there's a Z0 where the local gradient, when we differentiate F of Z with respect to Z is 0. And now let's use another familiar tool, basically Taylor expansion from calculus, and expand log of Fz at the point Z0. Right, from Taylor expansion, we remember how Taylor expansion works. So if we have a function g of x, like being expanded at, let's say, g of z, at z0, we have g of z0 plus, like, essentially 1 or 1 factorial, that's 1, g of differentiated at z0 plus 1 over 2 factorial, well, plus the difference, z minus z0, twice differentiated. Confusing x and z, so basically the quadratic term involves the second order derivative of the function, right? So this is what's happening, right? So if we expand log of fz, we first have the value at z0, then we have the first order differentiation term. So note that, like, d of log of fz with respect to z is, according to chain rule, z 1 over fz, and then it's d of z. So the second term is 0 based on this, because it's a local mode. So therefore, the first order Taylor term goes to 0, and the second order Taylor term we simply denote it as 1/2 times a factor a times the second order term, the quadratic term. So, okay, our goal was to get to a quadratic log of q. Now we seem to be somewhere close to there, right? Except what is this a? And what is this minus sign here, right? So a is simply the second order derivative of log of fz with respect to z. And there is a negative sign here. It's worth noting that the original Taylor series have positive all around, and we define a as the negative second order derivative of log of fz, and put a minus sign in front. It's for convenience. Also, it's there because, in Gaussians, the sign in front of the quadratic term is negative. Therefore, that's the incentive for us to do it this way. Right. So if we take the exponentiate both sides of 4.127, right, we basically get a f of z is approximated by the value at the mode f z0 times this negative square exponential term, right? So that's Gaussian looking, but it's not quite yet a Gaussian distribution. So how do we make it distribution? We simply normalize. Right? If we, referring to the expression above, the normalization simply works out as a over 2 pi, taking the square root times this square exponential term. So that's easy. It's a bunch of like one-dimensional Gaussian arithmetic. What is interesting and worth noticing is that, so from this step to this step, like, so information about f of z0 and information about the original normalizing constant z is not needed. So the normalizing term of q of z is simply a function of a, the second order negative derivative, right? So here we assume that a is greater than 0, otherwise it's not a Gaussian. A stands for the variance and needs to be non-negative, or actually strictly positive. So that's in one dimension. It seems easy enough, and the picture is, well, there's another, right? This picture reminds us of what's happening. So the first picture is P of Z, and the second picture is minus log of Fz and Z. Right. So what we're doing is we take the original lopsided distribution, match the mode, and then use the negative second order derivative to decide the variance of the resulting Gaussian, which is this particular line, which is quadratic in the log space. And when converted to the original space, it becomes Gaussian. Right, simple enough. Okay, question from Vikram. Do we lose of Z0 because the big Z has a factor of has these things in it? The answer, my answer is kind of no, because going back to the last page, what the manipulation on this page is doing is really that I'm Laplace approximating any unnormalized PDF function or any basically non-negative function that are bounded. We don't even, right, so in principle, right, we would have f of z naught because we need to solve for z0 somehow. But we never need to know z. That's the curious thing about it. If you have a somewhat ill-defined, unscaled PDF function, you can still Laplace approximate it. Right. What if what we found is a minimal point? That's a good question, Qinyu. Then try again. Try and find a different stationary point until you get a greater than 0. We cannot do Laplace approximation around a point that is not a local maximum, unfortunately. Yeah, we'll come back to that after we talk about the high-dimensional version. So hopefully the picture is easy, right? So here is the vectorized version. So instead of differentiating now, we write the gradient symbol, right? So we have still f of z. So the high dimensional, like in the vector space, we still have p of z equals to the bz times f. Why am I? Do I keep writing x? F of z as a vector, and it has a stationary point still called z0. And we do the same Taylor expansion. The front part is exactly the same. The only difference here is we still have the negative minus a half quadratic term, except in vector notation, this term is now sort of a vector inner product modulated by A. Right, so this is a matrix, and this is a vector. This is a column vector. No, the other way around, sorry. It's a row vector, that's a column vector, right? And the Hessian matrix, basically the second order derivative for vector input functions is simply, right, take the gradient of the gradient of log of fz and compute the value at z0. And we now do the same thing, right? We exponentiate on both sides, and that gives us a function form that looks like a Gaussian again. So this term, right? So we now, from what we did on the last page, we need to basically, the next step is basically normalize this Gaussian distribution. And we expect the result to not involve f of z0, which is indeed the case. So here we go. This is the same equation on the bottom of last page. We use the definition of the Gaussian distribution, multidimensional Gaussian distribution to normalize. Again, the normalization factor only involves A, so it's square root of the determinant of A over this 2 pi factor raised to the power of m, the dimensionality of the variable. And this corresponds to a normal distribution centered at z0 with precision matrix A. All right. Again, it doesn't involve f of z0 or bz. Right. So coming back to the question between like Qinyu and requirement is discussing on chat. So Q of z is a valid multivariate Gaussian distribution if and only if A is positive semi-definite, or like in other words, z0 must be a local maximum. It cannot be a local minimum or a saddle point. That will not make a valid Gaussian approximation. So geometrically, it kind of makes sense, right? So we can't easily think in higher dimensions, but imagine x is 2 dimensions, and we have sort of a local mountain in the arbitrary function f of z. Yeah, so we can put a Gaussian, like sort of that's somewhat approximating that mountain. We cannot approximate, like put a Gaussian that to approximate a valley or a saddle point, which is something like this. Like it's higher on one side and lower on the other side. And what about this? Basically, the f of z is a landscape rather than one mountain. Then we could have different Laplace approximations for each mode. All right, so this is basically a Laplace approximation in a nutshell. We haven't done any new algebra. We simply said our goal is to put a Gaussian mountain around the mode of whatever thing that we're approximating. So what are the pros and cons of this thing, right? So in the vector space, the result of this is simply this expression copied from last page again. So it involves a z0, it involves an a, and that's it, right? So the good thing is that, hey, we don't need the normalization constant. That's a good thing. Another good thing that's stated here, but you will only see later on in this lecture, is that due to the central limit theorem that says when we essentially accumulate, or basically accumulate many data observations through the likelihood function, when we observe more and more data that is whose posterior distribution, like who makes the posterior distribution of weights non-Gaussian, the combined effect is that the posterior is increasingly better approximated by Gaussians. So that's a pretty remarkable point. Let's just say that, well, we started out by saying we're just gonna do this really simple thing, put a Gaussian mountain on everything that looks like a mountain. It's not actually such a bad idea. Right, and the condition for that is when we have, like in the Bayesian setting, if we have more number of observed data points, then the Gaussian approximation tend to work better. All right, so what are the potentially negative points for Laplace approximation? So it assumes the domain of the variable z implicitly is the same as the domain of the Gaussian distribution, which is the entire real space in however dimension. So if, for example, if we know our z is strictly greater than 0, we want positive random variables, then we might need to transform it into like log of z is enough. Of course, doing such transformation means compressing and expanding the dynamic range of certain intervals by a lot. Whether that is a good thing to do for your application is sort of, it needs to be decided case by case. Another thing is, so this approximation really doesn't care about what happens elsewhere besides the local mountain information, right? So imagine what happens is, we do this, right? So if I have a bimodal, let's say this is my z, and I happen to find a z not here, the Laplace approximation will actually put a pretty high mountain here. It's going to be qz, because the Gaussian approximation is normalized, and it assumes it basically matches the mode and computes the variance by normalizing this local second order with the local Hessian matrix. And it assumes this q of z integrates to 1. So it completely ignores the higher mountain elsewhere that the local mode finding wouldn't have a way of knowing anyway. But because, again, central limit theorem, when we have lots and lots of accumulating distributions, this won't happen. They're like the distribution tends to be Gaussian, we're likely just going to like congregate against the higher mode. But finding the higher mode is another question, which is not guaranteed. All right, so that is what is Laplace approximation in general. Let's now use it on something we have learned earlier this semester, logistic regression. So remember, we have started this semester pretty much by saying, oh, right. So we talked about linear regression, and then we immediately talked about the Bayesian version. And then we spent a chapter 4, or most of chapter 4, and for 2 hours talking about classification and different ways about thinking about classifiers. But we didn't talk about like the Bayesian version of classification. Similarly, right, so last week we talked about, let's say, GPs, Gaussian processes, as a regression tool. Similarly, we haven't talked about Gaussian processes for classification. And yeah, today is the session where we're going to resolve both of this because, well, there are two comments. Gaussian processes are generally Bayesian tools. And yes, we first cover how to be Bayesian for classification, or for the most popular classifier, logistic regression. And then we move on to Gaussian processes. There's a comment that people have done work to connect, kernel methods and Gaussian process to neural nets. So I thought it's worth talking about that as well. So to do that, because it's been a number of weeks, it's useful to remind ourselves what is logistic regression. You will say, oh, that's easy. Yes, it's very easy. It's basically a linear, the inner product of a weight vector with a feature vector phi passing through the sigmoid function called sigma. Right. And the sigmoid function looks like this. It looks like this. It grows from 0 to 1, right, with 0.5 in the sort of in the 0 when the input is 0, right? So when we have a data set, the likelihood of a logistic regression model is as follows, right? So it's basically, right, when we 0-1 encode our classification label, we can write the likelihood in this exponentiating form, which we would be familiar with, right? So basically it's either sigma of W transpose phi or 1 minus sigma W transpose phi. Okay. For those of you playing with neural networks, you will come up with this cross entropy loss error function a lot in all sorts of classification tasks. And this is done by just doing the negative log of the log likelihood function. And we can also show that the gradient of this cross entropy error function is simple looking. There was a page deriving this. We didn't go through it in class. Components of it is somewhat useful, which we'll go through. And then you can, I'll leave you to go through some of the whole gradient derivation if you like. So, so to be Bayesian about it, we simply take the definition of the classifier, the error or negative log function, which we're trying to minimize, and slap a prior on it. And as we have always been doing, the prior on the weights is Gaussian, which means 0 and covariance S of 0. We know from Bayes' rule that the posterior probability of the weights, given a set of observations, targets, is like this, right? So it's proportional to the prior of the weights and the likelihood, right? So this is assuming P of t as a vector is constant. Right, so it should be divided by P of t, but given that the data set is given, then the probability of the data set is some constant that we don't need to compute. So in lots of machine learning derivations, you will see sort of constants thrown here and there. It simplifies the expression a lot, but whenever you see that, it's worth thinking about what goes into the constant, right? So for this 4.141, this proportional sign means there's a multiplicative constant, which is P of T. Then if we take the log of this posterior, we get two terms. The first term is, this is basically the quadratic part of Gaussian. Of the normal distribution, let's say, multi-n distribution. And the second term, this one comes from E of W directly. And this constant now has two parts, right? It's the normalizer of the Gaussian distribution. And then the second part is P of T. Two constants that we don't really care about, we can lump them together. Okay. So what did we just do? We were just being Bayesian and wrote out some analytical form of the posterior distribution of the weights given data. And now, starting from this equation, let's work out the next step. The next step is to use the Laplace approximation recipe that we just learned. You might say, wait, what exactly are we working on? Do we really need Laplace approximation, right? So for anything non-Gaussian, I argue that, well, let's Laplace approximate because it's this class that we're learning about it. So to convince ourselves that this thing is non-Gaussian, so log of the probability is a quadratic term. For it to be Gaussian, the whole thing needs to be a quadratic function of W. This is not true because, look, so Tn's are constants, they are observed, and log Y's are essentially log of sigma W transpose Phi's, right, Phi N's, right. These sigma functions, they are not quadratic or linear, plus we're taking a log on it, right? So to be more precise, what we're computing is log of 1 over 1 plus exponential of W transpose Phi. Right, so this is clearly not quadratic. There are minus sign that I missed. Yes, there is. Yeah, let me do this. Okay, so this justifies the use of the Laplace approximation recipe. Now what do we need to do? So the first step is compute the local max. And the second step is compute Hessian around this point, right? Around the Z0. So the first step, well, we have a posterior error function and we know how to do gradient descent, or call PyTorch or JAX. AutoGrad, one of these modern tools. It will do it for us. And hopefully it gets to a maximum, not a minimum. We could check that. So assume we could do that. Then what is the Hessian of this posterior? So let's stare at it and convince ourselves that the expression here is reasonable. So what I'm trying to do here is, instead of going through the derivation of the Hessian, let's just intuitively check that it's the correct form. To do this, so the quadratic term, if we take the second order derivative, it becomes a constant, right? So, so when we differentiate once, this a half in the front goes away. We differentiate the second time, like w minus mean, the mean term goes away, and it's w is simply multiplied by this inverse precision of the prior. So this term comes from the quadratic term, right? Differentiated twice, we get that. And you will see, you will ask, oh, so then what's the next term? Next term comes from the negative log likelihood function. So it's worth noticing that there's this expression worth knowing for the sigmoid function. When we take the first order derivative of a sigmoid, it is actually the sigmoid itself multiplied by its converse, 1 minus the sigmoid. And that is what's happening in the second term. So again, the TNs are constants. So and you will say, okay, we are differentiating with respect to W, right? So this is with respect to W. For example, Tn log of Yn. And the W is hidden inside the Yn, right? So we should replace it. Writing W transpose phi, let's do that. Right, for example, the first term here. Let's say term A here. When we take the differential, when we differentiate, it looks like this. And using the result of differentiating the sigmoid, we can get, so Tn is constant, and then we essentially have sigmoid W transpose phi n, that's itself, times 1 minus sigmoid W transpose phi n. Right, that's the first term. The second term can be expanded similarly. And we have the log, right? So the thing about the log in chain rule that I forgot is there's this additional term here. And these two terms cancel out. And we're left with Tn times this. And then you can do the similar thing with the second term. The result is that we have, there's an additional phi term, right? Because we're differentiating with respect to W, so we end up with a phi n. What we could do is to verify, right? So this y times 1 minus y will show up when we differentiate once more, because we're applying this same formula again. Log vanishes after the first order derivative. And then phi n, basically, each time we take the derivative, we multiply the thing by phi n. And because this is a matrix, we do the outer product of phi n rather than the inner product, right? So that seems reasonable. You could also derive this by essentially building onto from the previous result of differentiating. You can say, if we assume the first order derivative in this error function term is this, then we differentiate this once to get the second term in 4.143. In other words, all of this exercise, so it's do this or get this term from here, gradient ones. This is to convince us the Gaussian approximation or a Laplace approximation to the posterior of logistic regression, the width of that or the variance, the covariance matrix of that is the original covariance matrix, or yeah, plus a term induced by the data. So that seems reasonable. It doesn't mean that the covariance is necessarily sort of bigger in high dimensions, because the data points, the covariance of them can cancel each other out. So here's a picture to enforce what we said, and also the point about central limit theorem. So here's a prior of a one-dimensional weight, which is, yeah, standard Gaussian. And here's a posterior of this wave vector given a data which is only one dimensions. So it's 10 and minus 20. So the true posterior is like this. It's lopsided because it's a Gaussian multiplied by a sigmoid. And the sigma is not centered around 0, so it's a sort of lopsided for that reason. And if we compute a Laplace approximation, oh, it's the blue one, sure, it matches the mode and normalizes itself to 1. So it doesn't match, for example, the perceived spread of this original distribution at all. Now, so in this other example, so there are 500 data points from a logistic regression model with no bias. And the weight prior is still standard Gaussian. And now there's this multiplicative term. So as we can see, the prior of the weights is really spread after seeing 500 data points. The posterior, given the data, the true posterior is actually quite symmetric looking. And if we fit a Gaussian tool using the Laplace approximation, we cannot essentially eyeball the difference. So this is pretty good. And this is due to CLT, thanks to CLT. So hopefully this convinces you that Laplace approximation is somewhat useful, especially in the logistic regression case. And you would say, then what does this allow you to do? It basically allows you to estimate the mean. So it not only gives you one map estimate of the weights, but also allows you to compute your distribution of the weights, right? Put a confidence interval in your weight estimate. It also gives you a confidence interval for your predictions automatically. To see that, so the predictive distribution, which we won't derive, there's a couple more equations before we can get there. This is a picture of how it looks like. But in general, let's just remind ourselves, predictive distribution, as we've been looking at in regression, is basically probability of the target given data point and the observed targets. Right, and if we use the Laplace approximation, so this is the, we can have some Q other than P. Right, so the second term is the posterior, so we can, let's say we can approximate that. And moreover, this could be viewed as basically a convolution of the sigma term, which is the nature of the logistic regression, and this Gaussian term, which is by nature of the Laplace approximation. So the picture on the right shows basically for a data set, pre-decided toy data set of 10 points, squares and stats. If we fit an optimal weight, whether it's map or maximum likelihood, it doesn't say. Then the classification, let's say probabilities and landscape look like this, right? So no matter what W star is, the contours have to be linear. Basically, for a unit distance that we're moving from the separating hyperplane perpendicular to the hyperplane, the decrease in probabilities is the same. If we compute the predictive distribution of Bayesian logistic regression, on the other hand, and then connect the similar, like this points of the same value to compute the contour line, it looks like this. So that's what I guess Laplace approximation on logistic regression can give us. Namely, right, we could do this numerically, but having a Laplace approximation, you could essentially in analytical forms approximate these posterior and predictive distributions, and it allows us to draw the whole landscape of essentially class distribution and how confident we are in terms of assigning the class label all through the space. We can intuitively convince ourselves that this curved landscape is somewhat reasonable because the decrease, or basically the uncertainty, basically for a decrease of a unit probability in predictive in probability of class 1, the gap is sort of narrower around the known points, but wider in unknown points. In areas where there's no training point, right? Because in these regions where we haven't observed data points, we really don't know. And what we assign as class 1 or 0 is less good or less confident, or sometimes not better than random guess if it's really far away. So the same observation was true for Gaussian process regression, if you remember, right? When we go outside of the interpolation scheme and go outside of the training points, the uncertainty cloud increases by a lot. So that's the expected behavior. All right. So that is Laplace approximation, how to use it on logistic regressions. Are there any questions? Oh, yeah. Vikram said, the left-hand side graph is a Laplace approximation, and the right-hand side graph is predictions with some optimal weights. Yes, you're right. So both of these contour lines refer to right, okay, good question. So this one, it assumes, so the right-hand side picture assumes it doesn't actually do the integration upstairs. In other words, it assumes that the probability of the weight given the data is a delta Dirac function around the optimal weight. And when we integrate, we basically just substitute in the like essentially it is a landscape, right? So this is essentially a landscape of sigma of the optimal weight over right input x1. So in this plot, phi is simply two-dimensional, and it's x1, x2. Yeah. And in this case, if we imagine slicing this sigmoid function, it will go something like this. So it will be, let's say, low on the left-hand side and rises and hits 0 here, rises over here. So the right-hand side is a point estimate, not an integral over possible weights. The left-hand side is an integration over possible weights done over Laplace approximation. I hope that makes some sense. So we haven't addressed, in this particular picture, we really haven't addressed whether Laplace approximation is good. For this purpose, we just say, right, if you compute Bayesian classification, this is the kind of picture you get. Whether it's being a Laplace approximated or computed in some other way, this slide don't really say. All right, thanks for that question. Now let's come back to Gaussian processes. All right, let's do this. There's a small change of notation. So we now denote, last week was y of x, isn't it? Right. Anyway, so this week is a of x. Let's say we have input x, and there's a so-called latent function a of x. And it's a Gaussian process of mean function 0 and covariance function capital K, which takes 2 arguments of x and produces a number, which you can think about as similarity. So the training set is again a set of x's and a set of target variables that are either 0 or 1. And the task, so the mapping between the underlying Gaussian process A and the target variable is simply through a logistic, a sigmoid function. So if t equals to 1, basically class 1, the posterior of t given A is sigma of A, it's 1 minus sigma of A otherwise. Right, pictorially what this means, so given a set of different x values in 1D, in this particular case, we can sample Gaussian process instance A and draw it like that by just running our multivariate Gaussian sampler, let's say. And then we just convert A to t by running a sigmoid function on each point. So if we look at these two graphs, we will be able to see that, well, yes, the local minimum correspond to the local minimums in here, and the local maximum will correspond to the local maximums, but trivially speaking. But let's say the fluctuation is less, and if we read the axis label, we'll see that the dynamic range of this function has been squished to within 0 and 1. It's defined by the sigmoid function. Okay, so that's easy enough. We haven't really done anything new. We just take a Gaussian process, slap the logistic regression output function onto it, and call this a Gaussian process classification model. All right, great. Once we have stated this model definition, now we need to solve 2 questions. One is how to learn. The other one is how to predict. Before we answer that, let's just say what we just said once over. We said we have a set of observations, training input x1 through xn. this intermediate variable A depends on them in the fashion of a Gaussian process. And then we pass A through a sigmoid function, we get a target variable. So from X to T, it's not a Gaussian process anymore because of this sigmoid function nonlinearity. Right, so let's try and remember what we know that could be useful. Okay, we know Gaussian process regression, so from X to A is a regression. And in the last week, we can just import a result with a notation change, right? So last week we've been calling the output T's for good reason, and then now we just rename them as A. And we write the same expression. The prior distribution of the first n+1 A's are essentially a Gaussian process of mean 0 and covariant function big C, subscript n+1 denoting size. So if we remind ourselves, last week we've been looking at essentially C's that are essentially the kernel function over the data points, plus some inverse of beta times, like on the diagonal. That will keep C being well behaved or nicely conditioned in linear algebra terms. In this section, we assume actually A is noiseless, right? So in last week, we assume C, yeah, okay. It's the same notation, xn is k of xn plus beta delta n. Right. So this is the noise term to map between the Gaussian process and the output. In this lecture, because this A is an intermediate representation, from A to T, there's some noise anyway. We don't need to explicitly account for the noise. But the claim here is that it is a good idea to add this regularized term anyway to keep the C nicely conditioned. All right. I think this is a minor point, but sometimes it's useful to think about why we're adding it, whether it's part of the model or whether it's for numeric stability. As in the case of Gaussian process regression, training is sort of implicit. Once we computed the covariance matrix C, it seems that that's all the information we need to manipulate this. So let's just assume so and examine how we do prediction. So given the first n instances, we would like to compute the probability of the next instance having the label 1. And right, so the assumption of this whole slide is x n+1 is hidden, or 5 n+1 is hidden, and the first n data points x is hidden inside kernels k and c. Okay, so we want with these. And we know that from the new A maps to the new T with a sigmoid function trivially. If we plug in the results from Gaussian process regression, basically given the first n data points and their mean covariance matrix, what is the mean and variance of n+1 like output as a function of the input, right? So these were two equations we used a lot last week, just to remind ourselves. We do the same here. Basically, given the first n input and the intermediate variable, the n+1 in A is basically directly plugging in this with replacing well, k is the same, c of n is the same, replacing t with a of n, as we did 2 slides ago. With these components, we can unroll the target expression using Bayes' rule. Basically, instead of computing t n plus 1 equals 1, we compute the general probability of this and a sub n plus 1. And then we marginalize out a plus n plus 1. So this is assuming that, so we can break down the joint distribution into 2 pieces. This assumes basically Tn plus 1 is independent of Tn given An plus 1. This is a valid assumption because Tn plus 1 only depend on An plus 1 once we know that through those, like the logistic output function. All right. So we are going to be working with this expression for a while. The next 3 slides or so, and break it down further. So now we end up with 2 expressions and an integral. It doesn't seem to have helped in the first instance, right? So what we basically try and plug in things that we already know how to compute, right? So for the first term, it's essentially the sigma of An plus 1. So we know how this works. So maybe we can leave it for now. The second term, it involves T of Tn and An plus 1. What we really want to use is the GP result, basically the predictive distribution of the Gaussian process regression involving the A's, right? So we don't have that yet. How we do it is because we don't have A of n in this expression, we first find a way to plug it in. One way to do it is to just simply add this vector as a variable and then integrate it out, right? Once we do that, we use Bayes' rule again to break apart the 2 variables, right? Right, we also invert the distribution. Again, P of Tn is a constant. That's why it gets taken out. But we will actually put it back later on anyway in this expression. So we manipulate this. This first step is simply Bayes' rule. The second step has one more assumption. Basically assumes the probability of Tn only depends on the block phase An and does not depend on An plus 1, given An. This is reasonable because of, well, the output function relation, and also it's reasonable to say that I have a training data, the probability of observing output only depending on the training data and not the test data. Right. So the second step follows from here. And at last, what we still have an integral over the block An, but now we would have a term that is exactly what we want. The predictive distribution of GP regression used over the A's. We had this expression 2 slides ago. We're just gonna put it back here. And the second term, which is probability of An given Tn. Okay, that's strange. We don't know how to deal with this one. We say, maybe we can Laplace approximate this. So this is the predictive distribution that we try to get. We first expand it using an integral. We then expanded one of the terms into another integral. So we're double integral at this point. And now we finally get a term where we can try and plug in Laplace approximation. So let's do that. In order to do so, we also notice this particular term is not in the form that we love to work with either, because we know that P of Tn given An, this is, well, logistic regression. But the other way around, it's not. So but we know the prior of An is Gaussian. It's Gaussian process. And then we just flip it, right? So we walked through this almost exact path in the logistic regression section. So basically, we can approximate the posterior of this GP classification as a combination of, log of P of An plus log of this logistic term. What this is missing is minus log P of Tn, right? But this we already said is constant. We're not going to write it in here. So the first term is a Gaussian process, therefore it results in a quadratic term of An plus a normalizing factor that gets absorbed into the constant given the data set. And then this, right? And then there is the determinant of Cn is part of the normalizer plus a linear term. So where do this linear term come from, you might ask? It is from taking the log of this bit. So the logistic term converts into this plus the second term. Remind ourselves that, well, the sigma function is nothing but 1 plus An. So it goes like that. So you might, at this point, you might ask, wait, what? So we're familiar with this first form of logistic likelihood over n in the IID data points. To get from here to here, you just essentially expand and simplify. And things cancel out nicely. Let me just say that. So yes, you're expected to do this kind of expansion potentially, but usually you'll get a hint if it's an exam. All right, so the psi of An term is what we got on the last page, which is quadratic term in A and a linear term in A and plus the sum of log of E, like this log of sigma terms. Okay, remember the 2 steps of Laplace approximation. Step A, find local max. Step B, compute this Hessian matrix as negative, like twice differentiated version of that. So let's just do that. Find the local max by, well, taking the gradient once anyway. We essentially convince ourselves by saying, oh, the quadratic term is here. The linear term results in the Tn. And then the sigma n is basically a vector of all the sigmas. That's reasonable, which is this, basically. This long term will become that. Right. The Cn vanishes because it involves data. Right. So from this, if we set gradient of psi of An to 0, we will like, and solve for a of n. So basically a n star is, well, we move this to the other side, sigma. So basically Tn minus sigma n as a vector. And then we need to multiply C, big Cn covariance matrix to cancel it out. So that's basically solving for the stationary point, which is basically this thing downstairs, written out in the book. Okay. And then we differentiate it further. This linear term becomes only the inverse of the covariance matrix. This term does not depend on A, so it vanishes. The sigma term becomes the whole matrix of W with the diagonal entry of sigma times 1 minus sigma. So this is the case because remember the D sigma D A is essentially sigma times 1 minus sigma. So plugging in that, we will get the definition of W. And it will have a value only when the two variables being differentiated twice are the same. When they're not the same, they become constant to the when you do the second time differentiation. So therefore, Wn is this big diagonal matrix. So this is the manipulation has a number of details in it, but I argue it's not too difficult, right? We just sort of need to. It's not difficult to convince ourselves to do it. Of course, doing it for a new, slightly different setting is it's more difficult. So the claim here is this, this negative second Hessian matrix needs to be positive definite. But this posterior distribution of A is non-Gaussian. So the Laplace approximation we get written as Q of An is a normal distribution centered around this A star that we just got with this posterior covariance matrix or precision matrix, which is Wn, we'll take the negative for both, Wn plus the inverse of C. So we already know that Cn's, because they are covariance matrices of Gaussian processes, they are positive semi-definite. Inverse of E is also positive semi-definite. W is, so another property of the sigmoid function is these things, they lie between 0 and 1 over 4, basically 0.25. It's maximum when its sigmoid is exactly at its middle point. So that is a valid Laplace approximation. All right. So one more question, Qingyu. Since sigma sub n depend on A of n, why should we write it down? Why could we write it down at the right-hand side? Good question. So here's the deal. It's non-obvious. So we have essentially x1 through xn. These are, let's say, assume we're working on a one-dimensional input space, so not worry about whether x's are vectors. They can be vectors. And then they map to A1 through ANs. These are not vectors. These are scalars. And then they map to the T's, T1 through TNs. So this is the training data. Or a model, right? So we can actually sample from this model. So the ANs are considered known. What is not known is the whole distribution of the ANs, given the TN. So exactly what did we want to approximate is this thing. So, no, let me put it better. So because ANs, they are latent variables, we can sample them, but so X and T's, XNs and TNs are known. So P of AN as a sort of prior, this is known. Yeah, I take it back. And now we want to compute this AN's condition on TNs. How can we write them down out? It's a good point. So sigma of AN should be actually probability of T, which we know, giving training data, whether it's 1 or 0 for sure. But doing so will force us to make these sigma n's 0 or 1, which I'm not sure is the right thing to do. Yeah, let me pack this. I'll get back to you after the class. So assume, okay, right, I'll write down the question. What do we use? Well, one option is to plug in the T's, but right, that will make both. It will make actually AN star 0, and then the H looks like it will be a valid H, but it will be a bit funny looking because it's just CNs with ones added sometimes. Yeah, I'm not sure at this point whether that's the right thing to do. So this is what we do to plug everything back. What we went through last was this part. So just to remind ourselves how we got there, we wanted predictive distributions. We break it into 2 parts. We approximate the second part, like already within the integral with another integral. We know how to compute the first part of that integral component in closed form. The second part gets a Laplace approximated. And then we combine these 2 Gaussians. Right, so what this amounts to is a convolution of 2 Gaussians. Or we can also plug in this basically conditioned Gaussian manipulation and compute simply basically the expectation and variance of the ANs given the training data. The latent variable linear variance. It's Gaussian, so we approximate it with this Laplace approximation. So that's Gaussian. So with that expression, so remember so far we haven't solved really, like we've only solved the second part here. We haven't solved putting this back together and doing the outer integral. And to do that, we basically plug in this approximated Gaussian distribution of an plus 1 given Tn's with the sigmoid. And you stare at that, and you ask yourself, what does, right, so what is the convolution of between a sigmoid and a Gaussian do? The book basically has a trick to, again, approximate this sigmoid with a probate function, and then there is and then convert it back to a sigmoid, which you're not required to memorize or know, but just know that you could approximate this with in reasonable position with another function, basically sigmoid times a kappa function, which is essentially the normalizer between the approximated probate and sigmoids. It's a function of sigma squared for this Gaussian component of this integral. It is not, I should say, it's not, it's not super intuitive, but hopefully the picture helps. What this does is there's two-dimensional input, x1 and x2, and a whole bunch of training data. The Gaussian process decision boundary, we just draw the contour of the decisions, or the probability of t equals 1 is 0.5. It's black. The ground truth boundary for generating the data is green, and the estimates are shaded in blue and red. So this is basically computing Tn plus 1 given Tn for essentially Tn plus on the grid. Or for actually x1, x2 on the grid. So just remind ourselves, right? So what we can compare this picture with is the logistic regression one. With Bayesian logistic regression, we are able to essentially produce confidence intervals that sort of tell us how far away we are from existing training data and how confident we are with the current estimates. So what Gaussian process regression does is that it sort of takes this to the next level, so the decision boundaries are no longer linear anymore, and now we can have arbitrarily shaped decision boundaries and still have this confidence into estimates when we do classification. All right, I think we're almost done for today. I know it's a fair bit of content, and especially the GP classification part is kind of long. I would say overall, I will treat this as a culture approximation for Laplace approximations rather than expecting people to reproduce the Laplace approximation and how exactly to do it for GP classification end to end. I feel like in this course, there's probably not much headroom for that. But if you can follow the process and see how it's done and convince yourself that, well, this is the way to do nonlinear classification in a Bayesian way, I feel that's good enough. And you might get asked in the exam to critique the properties of Laplace approximation, reproduce a few for simpler distributions, and so on. Right, so with neural networks, right, so we promised to come back to neural network. Here we go. So if we assume a two-layer neural network with big M number of hidden units, and this is sort of a general neural network that can represent any function on Rn. And we haven't really talked about Bayesian neural networks, and let's not get there in depth, but assume we can just make it Bayesian by putting a prior over W, like we did a number of times by now. And we can intuitively think about a simplified neural network is I draw the input as one dot, and then I have, let's say, m number of hidden units. There's m of these, and then there is, let's say, one output, which we write as a function of the input and the weight. Right, so this is what the neural network function f of x comma w stands for, and we have a prior over the weight. So there's lots of the fundamental results of this has been done like over 20 years ago, right? So Rafferneal in 1996 have shown that for a broad class of prior distributions, or P of W's, the distribution functions generated by a neural network, so the like f of x will tend to a Gaussian process when m is infinitely wide. So this is an interesting statement. So basically, if we put a prior on W for many different types of priors, and we make the network infinitely wide, meaning that the network can actually represent any any continuous function with, let's say, probit and Gaussian activations and so on, the output function distribution is a Gaussian process. Interesting. And people, Neil and others, have also shown that the covariance function for this neural network-induced Gaussian process is non-stationary. So so examples of stationary. So as we said, so most of the time in these two classes, we are dealing with not only stationary but also isotropic kernel covariance functions, namely the squared exponential, right? So for example, exponential of minus some length scale L over 2x minus x. But non-stationary, so what is a non-stationary kernel that we often see? For example, the inner product kernel is one of them. I'm not saying in the limit it is that, but when we try and visualize or think about a non-stationary kernel, this is the simplest example. And the last comment is so what does the weight prior has to do with the resulting Gaussian process in ways that we know how, like, that we can think about Gaussian processes, right? So the weight prior determines the length scales of the neural net function or Gaussian process in the limit. So here are some examples. This was pulled out of chapter 5, the neural network chapter of Bishop. So what basically this does is, right, so a single input, a single output, the neural network has one input, one output, and 12 hidden units, exactly like what we drew last time. So basically, there's 12 this and this, right? So this is what the neural net looks like, f of xw. And then alpha 1 of b, this is bias, right? So these alphas are precision variables. So precision high, right? So higher alpha meaning like varies, right? So the corresponding parameter varying faster, or the square exponential decays faster. So the A sub 1 super B is the prior inverse covariance, inverse standard deviation for the bias of the first layer, and this is the bias for the second layer, and the weights for the 12 hidden units share the scale parameter that are superscripted W. All right, so if we set all of them to ones, basically standard normal, we get this, and we sample the function f of x comma w, we get this. So between the first picture and the second, we see that we change the weight prior of the second layer, but holding everything else fixed. That doesn't have much of an effect, right? And we're only changing it by 10 times. If we change the weight of and bias parameter by the first layer for the precision to be a lot bigger, namely the standard deviation of the weight prior distribution is a lot smaller, we get a lot more jaggy functions, right? Similarly, so what happens, right? So that there's a subtle difference between just changing the weight and also the bias. So the bottom two pictures are a lot more jaggy. Like the scale of the same magnitude of change is a lot shorter than the top two pictures. So that is what we could read from this. Right, and there's this book makes the comment that the weight prior in the first layer covers the horizontal scale of variations, and the bias prior governs the horizontal range over which variation occurs. Right, so if we make this bigger, then the variation sort of occurs in a longer time and doesn't fall back, right? Right, and then it argues that the parameter, well, basically the bias on the output governs the range of the vertical offsets. That is reasonable. So that's all we needed to say. We basically looked at Laplace approximations 3 times, looked at Gaussian process for classification, and briefly commented on why we should learn about this in the age of neural networks. Any questions? If not, so that's it for today. Yeah, thanks for turning in.